The wind cut different at 10,000 feet. Henry Schmidt learned that his first November in the Colorado Rockies in 1895, when ice formed inside his neighbor's log cabin walls and water froze 3 feet from the fireplace. John Miller and the other prospectors had built their cabins exactly the way every mining manual said: tight pine logs, mud chinking, stone fireplace, standard and trusted. By December, their cabin barely reached 50 degrees while burning through cord after cord of wood. Across the high country, miners fought the same losing battle in cabins built by the book and failing by the season. The prospectors mocked Henry when he erected what looked like just a canvas tent. Over the next 3 months, Henry quietly applied techniques borrowed from older traditions that kept his shelter 45 degrees warmer than their log cabins while using half the wood. What did he understand about trapping heat that every serious builder should know? The narrow gulch where Henry Schmidt staked his claim in late October of 1895, cut through steep slopes of pine and fir at 10,000 feet elevation, with scree benches that caught early snow and held it. The short building season before the winter freeze meant every prospector faced the same urgent choice: throw together shelter fast or abandon the claim until spring. Mining camp literature from Colorado to Montana spelled out the standard wisdom in black ink. Build a small log cabin during the fall months, fell pine or spruce nearby. Stack them horizontal with chinking of moss or mud. Add a simple woodshed and small stove. The reasoning seemed rock solid to every miner who had wintered in the high country. Log cabins were quick to build if you knew basic notching, familiar from childhood stories of frontier settlers, regarded as durable enough to last a full winter season, and represented a real house rather than the helplessness of canvas in a blizzard. Supply contractors and mining companies expected cabins when they calculated winter provisions, budgeting $200 or more in labor and hauling costs, but viewing the expense as an investment in a proper shelter that could house multiple men through the brutal months ahead. 6 prospectors working the adjacent claim demonstrated this accepted method with methodical precision. They felled lodgepole pine in early October, notched the ends with hand axes, and stacked the 8-inch logs horizontally with careful attention to corner joints. They chinked the gaps with a mixture of pine pitch, moss, and creek mud, built a stone fireplace against the gable end, and added a woodshed stocked with 2 months of split timber. The completed cabin measured 12 by 16 feet with a shake roof and cost them $40 each in materials plus 3 weeks of labor that could have been spent digging ore. By mid-December, when Henry's pocket thermometer registered 5 degrees Fahrenheit at dawn, the interior of that textbook cabin struggled to reach 50 degrees despite continuous feeding of the cast iron stove. Frost formed along the chinking where gaps had opened after the logs seasoned and shrank, and drafts cut through poorly fitted corner joints that seemed tight during construction but loosened as the wood contracted in the dry mountain air. The stove consumed 2 full cords of firewood each month, requiring daily trips to the woodpile that interrupted mining work. Yet the heat seemed to vanish into the walls and floor as fast as the flames could generate it. Worse problems emerged as winter deepened. Snowdrifts piled against the north wall until they reached floor level, and since the cabin sat directly on bare ground with no foundation or floor insulation, cold rose steadily through the plank flooring. The 6 men complained constantly of chilled feet, even when wearing heavy boots indoors, and condensation from their breath and cooking froze on the interior walls each morning. By January, rot had begun creeping into the log ends where they touched the ground, and several chinking joints had fallen out entirely, leaving finger-wide gaps that whistled with every wind gust. Henry Schmidt brought a different perspective to the shelter question, shaped by experiences the other miners lacked entirely. In his late 40s, he had grown up in a German immigrant mining family in the Midwest, where winters hit minus 20 degrees Fahrenheit regularly, and his grandfather had taught him that insulation beneath floors mattered as much as thick walls. During his years working Montana timber camps, he had observed how Army surplus Sibley tents used inner liners to create insulating air spaces, and he remembered reading detailed descriptions of these double wall systems in military manuals that emphasized trapping dead air rather than relying on material thickness alone. More significantly, Henry had spent 2 seasons working alongside a Ute scout who described how Plains tribes layered dried grasses and pine boughs beneath lodge floors and around wall bases to intercept ground cold and wind infiltration. This traditional knowledge contradicted everything the mining manuals recommended, but Henry had watched immigrant farmers in his home region use similar techniques with straw packed between barn floor joists, and the results spoke for themselves in reduced feed costs and healthier livestock during harsh winters. The social friction began immediately when Henry announced his intention to winter in a canvas tent rather than joining a cabin building crew. John Miller and the other prospectors viewed this decision as either dangerous inexperience or lazy corner cutting that would end in disaster. They warned him repeatedly that he would be begging for cabin space by December when his tent collapsed under snow load or his inadequate heating failed during the first serious cold snap. The general attitude reflected mining camp culture where following established methods meant survival and innovation meant unnecessary risk that could kill you. Henry quietly set aside the money other miners spent on cabin materials and used the time they devoted to construction for continued prospecting work that extended his digging season by 3 crucial weeks. He erected a heavy canvas wall tent measuring 12 by 16 feet, the same interior dimensions as the standard cabin design, but mounted it on a raised platform of rough-hewn logs rather than placing it directly on the ground. His sheet iron potbelly stove cost $8 compared to the cast iron models the cabin builders preferred, but weighed half as much and heated up faster with less fuel consumption. The most unusual element of his initial setup involved digging a shallow trench 6 inches deep and 8 inches wide around the entire perimeter of his tent platform. Other miners assumed this was some kind of drainage system, but Henry filled the trench loosely with pine boughs and dried grass rather than gravel, creating what he privately called a cold air sink, based on the Ute Scout's description of how mountain winds behaved around properly designed winter camps. He lined the log platform with loose hay gathered from a meadow 2 miles down the gulch, creating an 8-inch insulating layer beneath his canvas floor that no cabin builder had attempted. The setup looked makeshift compared to the solid log walls and stone chimneys of the neighboring structures, but Henry understood that appearances meant nothing if the underlying principles were sound. He had not yet implemented his full insulation system, holding back the double wall design and advanced techniques for later refinement, but even these initial modifications represented a fundamental departure from accepted frontier wisdom. The central conflict had crystallized into 2 opposing philosophies of winter shelter. The established belief held that structural mass and thickness determined survival, that solid log walls and heavy construction materials created safety through sheer physical presence that could withstand whatever nature delivered. Henry's emerging approach prioritized systematic heat retention, minimal air infiltration, and ground isolation over impressive appearance, betting that intelligent design could outperform brute force construction in the harsh mathematics of high-altitude winter survival. As November deepened into December of 1895, the fundamental flaw in the standard cabin construction revealed itself through the floorboards. The neighboring log structures sat directly on the native soil with no foundation beyond leveled ground, and their plank floors provided no barrier against the steady upward migration of ground cold that sapped heat faster than any draft through the walls. John Miller's cabin lost an estimated 3 full cords of additional firewood because cold air infiltration beneath the floorboards created a convection current that pulled heated interior air downward and out through gaps around the floor edges. The problem compounded as winter progressed and frost began penetrating 18 inches into the mountain soil. Frost heave shifted the corner logs upward by as much as 3 inches, widening the gaps that had seemed tight during construction and creating new pathways for cold air to enter the living space. Miller and his partners reported interior floor temperatures of 24 degrees Fahrenheit at midnight, when Henry's pocket thermometer showed the same external conditions, and occupants complained they could not walk barefoot across their own cabin floor, even when the stove glowed red-hot 3 feet away. Structural damage accelerated the heat loss as winter storms battered the exposed foundations. Several cabins suffered charring around their stove flues where the intense heat differential created expansion cracks in the logs, and one structure required emergency midwinter repairs when a corner post shifted enough to create a 4-inch gap that could not be sealed with available materials. The repair cost $20 in supplies that had to be hauled up from Leadville, plus 2 days of labor in sub-zero conditions that left one miner with frostbitten fingers. Henry's solution drew directly from his grandfather's barn construction techniques in the German immigrant communities of the upper Midwest, where livestock survival depended on keeping stable floors warm during prairie winters that regularly hit minus 30 degrees Fahrenheit. His grandfather had installed straw mat insulation between barn floor joists and used hay packing beneath haylofts, explaining that cold air was heavier than warm air and would always sink toward the ground unless physically blocked by dead air trapped in organic material. The technical implementation required precision that mining manuals never addressed. Henry constructed his log platform using 6 by 8-inch rough-hewn timbers spaced exactly 24 inches on center, elevated precisely 8 inches above the native soil to create an air gap that prevented direct ground contact. Over this framework, he laid 1-inch pine planking, then spread an 8-inch layer of loose dry hay gathered from the meadow grass that grew in the protected valley 2 miles below his claim. The hay selection proved critical to the system's effectiveness. Henry chose only stem material that had dried naturally on the stalk, avoiding any hay that showed signs of moisture or mold that would compress under weight and lose its insulating properties. He packed the hay loosely rather than tamping it down, understanding that trapped air provided the insulation value rather than the hay itself. And he left small gaps every few feet to allow air circulation that would prevent rot without creating thermal bridges. The perimeter trench system required more sophisticated engineering than his initial rough excavation suggested. After observing how wind behaved around his tent during the first major storm in late November, Henry deepened the trench to exactly 6 inches and widened it to 8 inches, then filled it with alternating layers of pine boughs and dried grass in a specific pattern he learned from a Ute wood gatherer who had described traditional winter lodge construction. The wood gatherer had explained how cold mountain air behaved like water, flowing downhill and pooling in low spots, and how native camps used strategically placed depressions to trap and settle incoming cold air before it could reach the living space. The pine boughs slowed the airflow and created turbulence that prevented the formation of laminar cold air streams, while the dried grass provided additional insulation and absorbed moisture that would otherwise freeze and create thermal conductivity. Henry's most innovative addition involved creating a wind-facing apron on the weather side of his tent platform. He laid a gravel pad extending 4 feet outward from the platform edge and erected a windscreen of pine poles arranged in a chevron pattern that broke the supersonic gusts typical at elevation. This configuration reduced wind-driven pressure differentials that could force cold air under the platform and up through the floor, a phenomenon that mining camp builders never considered because their cabin floors sat directly on solid ground. A mining foreman named Samuel Reed, who supervised winter operations for a company claimed 3 miles down the gulch, provided crucial testimony about floor-related heat loss that validated Henry's approach. Reed had documented fuel consumption across multiple camps over 2 previous seasons and discovered that structures with poor floor insulation consumed approximately 40% more firewood than identical buildings with proper ground separation, even when wall construction and stove efficiency remained constant. Reed's measurements showed that cabins built directly on ground experienced interior floor temperatures 15 to 20 degrees colder than exterior wall temperatures, creating uncomfortable conditions that forced occupants to wear boots indoors throughout the winter. He had also observed that men working in such cabins developed chronic foot and leg problems from constant exposure to cold rising from below, reducing their work capacity during the critical mining months. When Henry tested his completed floor system during the first week of December, his pocket thermometer registered 48 degrees Fahrenheit at floor level at midnight, when the external temperature reached 5 degrees below zero. The neighboring cabin floor measured 24 degrees under identical conditions, a difference of 24 degrees that translated directly into comfort and fuel savings. The fuel efficiency gains proved even more dramatic than the temperature differential suggested. Henry's tent required approximately 1/2 cord of firewood every 10 days to maintain comfortable interior temperatures, while the standard cabins consumed 1 full cord over the same period despite achieving lower interior warmth. The raised platform and hay insulation system eliminated the thermal sink effect that drew heat downward into the cold ground, allowing the stove's output to warm the living space rather than the earth beneath the floor. By mid-December, Henry had logged 8 consecutive nights when his tent interior stabilized between 68 and 70 degrees Fahrenheit with just a half load of firewood and 2 hours of daily cutting labor. The contrast with cabin performance had become impossible to ignore, yet the neighboring miners attributed his success to luck with wind patterns rather than systematic engineering principles they could replicate in their own structures. By early January of 1896, the envelope failure of standard log construction had become impossible to ignore. The neighboring cabins featured 8-inch thick lodge pole pine walls that appeared substantial, yet their interiors struggled to maintain 40 degrees Fahrenheit when external temperatures dropped to 30 below zero. The expensive structures, costing over $200 each in materials and labor, suffered from a fundamental misunderstanding of how heat moved through building materials, with gaps between logs growing wider as the wood seasoned and contracted in the bone-dry mountain air. John Miller's cabin demonstrated the classic envelope problems that plagued frontier construction throughout the high country. Frost formed along interior wall surfaces where chinking had fallen out, and wind-driven snow actually penetrated through corner joints that seemed tight during construction but opened under thermal cycling. One morning in mid-January, Miller found a 2-inch drift of powder snow across his cabin floor that had blown in through gaps he could not locate or seal with available materials. Another miner attempted to solve the envelope problem using a single wall canvas tent similar to Henry's outer shell, reasoning that canvas would eliminate the gap issues that plagued log construction. His tent interior temperatures dropped to only 35 degrees on the same nights when the log cabins achieved 40 degrees, proving that material substitution alone could not address the fundamental heat loss mechanisms that standard frontier shelter design ignored. Henry's response to the envelope challenge drew from 2 distinct knowledge traditions that mining camp builders had never combined. During his construction of the floor system, he had encountered a Ute elder gathering pine nuts near the meadow where Henry collected his insulating hay. The elder described winter hunting lodges used in the high mountains, where hunters layered dried grasses and pine boughs between animal hide walls to create dead air spaces that blocked wind infiltration while trapping body heat generated inside the shelter. The indigenous technique contradicted everything Henry had learned about canvas tent construction, which typically relied on single wall systems that provided weather protection but no thermal insulation. The elder explained that the layering principle worked by preventing air movement between the inner and outer surfaces, forcing heat to move through the insulating material rather than being carried away by convection currents that developed in single wall structures. Henry's German immigrant family background provided the second piece of the envelope solution through barn construction techniques his grandfather had used in the upper Midwest. Livestock barns in prairie regions often featured double wall construction with straw packing between interior and exterior boards, creating insulated walls that maintained stable temperatures during winters that regularly hit -20 degrees Fahrenheit. The technique reduced feed requirements for cattle and horses by eliminating the need to burn extra calories maintaining body temperature in drafty structures. The technical implementation of Henry's double wall system required precise spacing and careful material selection that no mining manual addressed. He erected an outer heavy canvas tent shell using 12-ounce duck canvas treated with linseed oil for weather resistance, then constructed an identical inner tent shell positioned exactly 12 inches inside the outer wall at all points. The gap between shells was packed with loose dry hay to a depth of 24 inches, creating an insulating cavity that eliminated convective air movement while providing thermal resistance equivalent to several feet of solid wood construction. The hay packing technique proved more complex than simply stuffing grass between the walls. Henry learned through trial and error that the hay needed to be packed densely enough to prevent air circulation, but loosely enough to maintain its insulating properties, and that different hay densities were required at different heights to account for settling and compression over time. He used coarser stem material at the bottom of the wall cavity and finer grass toward the top, creating a gradient that maintained consistent insulation value as the lower material compressed under the weight of snow accumulation on the outer shell. The floor-to-wall junction presented a critical thermal bridge that could negate the benefits of wall insulation if not properly sealed. Henry extended his hay packing system down to cover the junction where his insulated floor met the tent walls, and installed a continuous strip of raw wool blanket at the floor seam to create a flexible gasket that moved with the canvas but prevented air infiltration. This detail eliminated the edge leakage problems that plagued log cabin construction, where cold air entered through gaps between floor planking and wall logs. Henry's stovepipe modification addressed another major heat loss pathway that conventional installations ignored entirely. Standard sheet iron stovepipes radiated enormous amounts of heat directly through their walls, creating strong convection currents that pulled heated air up the chimney and out of the living space. Henry fitted his stovepipe with a double jacket system that created an air gap around the inner pipe, reducing the outer surface temperature by approximately 40% and keeping more of the stove's heat output inside the tent. The insulated pipe system also included a sheet iron damper that allowed Henry to control the draft rate and prevent the rapid air exchange that wasted fuel in conventional installations. By slowing the flow of combustion gases, he extended the time that hot gases spent inside the tent envelope, extracting more heat from each load of firewood and reducing the amount of heated interior air that was drawn up the chimney. When Henry tested his completed envelope system during a severe cold snap in late January, his interior thermometer registered 72 degrees Fahrenheit at dawn, after a night when external temperatures reached -20 degrees Fahrenheit. The neighboring log cabin achieved only 48 degrees under identical conditions, despite burning 3 times as much firewood over the same period. Henry's tent required approximately 1 cord of split pine over 10 days to maintain comfortable interior temperatures, while the standard cabins consumed 3 cords over the same period. The fuel efficiency difference represented more than a simple cost savings in a region where firewood had to be cut, split, and hauled by hand during the limited daylight hours of mountain winter. Henry's system freed him to continue productive mining work, while his neighbors spent increasing amounts of time gathering and processing fuel just to maintain barely livable interior conditions. Over the course of January, Henry estimated he gained 12 additional work days compared to cabin dwellers who lost time to constant fuel gathering. A 70-mile-per-hour windstorm in early February provided the ultimate test of envelope integrity when neighboring cabins experienced significant structural stress and interior temperature drops that forced occupants to abandon normal activities. Henry's double wall tent system maintained 65 degrees interior temperature throughout the storm, with the outer canvas shell absorbing wind loads while the insulated inner shell remained stable and draft-free. The performance gap had become so dramatic that even the most skeptical miners could no longer attribute Henry's success to luck or favorable site conditions, yet they remained reluctant to abandon the familiar log cabin approach for techniques that seemed too unconventional to trust with their survival during the remaining winter months. As February turned toward March of 1896, the seasonal transition exposed a critical flaw in both log cabin design and Henry's initial tent configuration that threatened to undermine the gains achieved through superior floor and envelope insulation. The neighboring cabins experienced wild temperature swings as spring weather patterns brought warm afternoons followed by plunging nighttime temperatures, with interior readings jumping from 80 degrees at midday to 30 degrees by dawn, despite continuous stove operation throughout the night. John Miller's cabin demonstrated the ventilation problems that plagued sealed winter structures when seasonal conditions demanded adaptive air management. During warm March afternoons, when external temperatures climbed to 25 degrees Fahrenheit, his cabin interior reached uncomfortable levels above 80 degrees, as solar heating through south-facing chinking gaps combined with retained heat from continuous stove operation. Yet when evening temperatures dropped back toward zero, the same sealed structure lost heat so rapidly that occupants woke to interior temperatures below freezing despite banking coals in the firebox. The condensation problems that emerged during the spring transition created health hazards and structural damage that mining camp manuals never addressed. Warm, moist air from cooking and breathing condensed on cold interior surfaces during temperature cycling, leading to frost buildup on walls and ceilings that melted during warm periods and soaked bedding and stored supplies. Miller reported losing approximately 1 bushel worth of dried beans and flour to moisture damage, representing significant food loss when supply runs to Leadville cost 3 days of travel time each direction. Henry's initial tent system faced similar challenges when uncontrolled air exchange created fuel waste and comfort problems during the transitional weather patterns of early spring. His insulated envelope system performed well during steady cold conditions, but warm afternoon sun penetrating the outer canvas shell caused interior temperatures to spike above comfortable levels, while unmanaged nighttime heat loss forced excessive stove operation that consumed fuel without maintaining stable conditions. The solution emerged from a conversation with the same Ute elder who had taught Henry about layered insulation techniques during the previous autumn. The elder described the critical importance of smoke hole management in traditional winter lodges, explaining that successful mountain camps maintain small fires with carefully controlled airflow rather than large fires with uncontrolled draft that wasted fuel and created dangerous temperature swings. The indigenous technique emphasized maintaining a small, steady fire with precisely managed air intake and exhaust that kept interior temperatures stable while providing fresh air to replace moisture-laden breath and cooking vapors. The elder explained that the fire's warmth should stay inside the shelter, not be drawn up the smoke hole by strong drafts that pulled heated interior air outside faster than it could be replaced by combustion heat. Henry implemented controlled ventilation through a system of adjustable openings that allowed him to manage air exchange rates based on external conditions and interior requirements. He installed a low-level intake vent measuring 6 by 4 inches in the outer canvas shell positioned on the leeward side away from prevailing winds. Fitted with a hinged wooden flap that could be adjusted from fully closed to completely open depending on interior air quality and external temperature conditions. The exhaust system required more sophisticated engineering than simple smoke hole management. Henry fitted his stovepipe with a removable sheet iron cap that included adjustable louvers, allowing him to control the draft rate and prevent the rapid air exchange that characterized poorly managed chimney systems. When external temperatures rose during spring afternoons, he could increase the draft rate to shed excess heat, while during cold nights, he reduced the draft to retain combustion heat inside the shelter envelope. The seasonal adaptation system addressed the fundamental problem that the same insulation configuration that provided comfort during extreme cold became excessive when external conditions moderated during spring transition periods. Henry developed a modular approach that allowed him to reduce insulation levels without dismantling his entire shelter system, maintaining structural integrity while adapting thermal performance to changing seasonal requirements. In early March, Henry removed the inner tent shell entirely during daylight hours when external temperatures rose above freezing, leaving only the outer canvas shell with hay packing partially removed from the upper sections of the wall cavity. This configuration reduced the insulating value by approximately 50% while maintaining floor insulation and perimeter cold air control that prevented ground-level heat loss during nighttime temperature drops. Henry also installed a removable wooden panel in the outer shell that could be opened during warm spring afternoons to create cross-ventilation that prevented solar overheating while maintaining the basic shelter structure. The panel measured 18 by 12 inches and included a mesh screen to exclude insects while allowing air movement, positioned to create airflow patterns that carried heated air out of the upper portion of the tent without creating drafts at floor level. The modular stovepipe damper system proved essential for managing the dramatic fuel consumption variations that characterize spring weather transitions. During a typical March day, when external temperatures range from 5 degrees at dawn to 30 degrees at midday, Henry could adjust his combustion air supply to maintain interior temperatures between 60 and 65 degrees throughout the entire cycle, while using approximately one-third the fuel required by neighboring cabins. Henry's ventilation control system eliminated the condensation problems that plagued sealed winter structures, while maintaining thermal efficiency that exceeded conventional construction methods. After 15 consecutive nights of below-zero temperatures followed by 2 thaw days in mid-March, Henry found no frost accumulation on interior surfaces or moisture damage to stored supplies, while neighboring cabins reported both morning frost on floors and damp bedding that required daily airing to prevent mold and rot. The fuel efficiency gains during the spring transition period demonstrated the importance of matching ventilation rates to thermal loads, rather than operating heating systems at constant rates, regardless of external conditions. Henry's March fuel consumption totaled approximately 1 quart of split pine for the entire month, while neighboring cabins burned roughly 2 cords over the same period, despite achieving less consistent interior comfort levels. The adaptive ventilation system also provided safety benefits that became apparent during a late March warm spell when several cabins experienced dangerous carbon monoxide buildup from sealed combustion systems operating during mild weather. Henry's controlled air exchange prevented the accumulation of combustion gases while maintaining thermal efficiency, demonstrating that proper ventilation management enhanced both comfort and occupant health during transitional seasonal conditions. By the end of March, Henry had demonstrated that systematic air management could extend the effective season of his shelter system while maintaining the thermal performance advantages achieved through floor and envelope insulation techniques, creating an integrated approach to mountain shelter that adapted to changing environmental conditions throughout the winter and spring transition periods. In February of 1896, a prolonged Arctic front descended on the Colorado high country that would test every shelter system to its breaking point. For 30 consecutive nights, external temperatures averaged minus 10 degrees Fahrenheit, with wind chill equivalents reaching minus 40 degrees as sustained gusts exceeded 50 miles per hour. Snow accumulation reached 3 feet in level areas, while drifting created banks up to 8 feet deep that buried entire cabin walls and threatened structural integrity throughout the mining district. The neighboring log cabins suffered immediate and cascading failures as the extreme conditions exceeded their design limitations. John Miller's structure experienced frost heave that lifted the corner posts by up to 3 inches, creating gaps wide enough to insert a man's fist between logs that had seemed tightly fitted during construction. The shifting foundation damaged the stone chimney, requiring emergency repairs during the storm that cost $20 in materials hauled from Leadville plus 2 days of dangerous outdoor work in life-threatening conditions. 2 other cabins in the immediate area developed structural damage when the accumulated snow load exceeded the bearing capacity of their shake roofs, causing ridge beams to sag and creating new gaps along the roof line that allowed snow infiltration directly into the living spaces. The occupants spent entire days shoveling snow from inside their shelters while attempting to maintain fires that consumed fuel faster than they could cut and split replacement wood in the brutal outdoor conditions. The fuel consumption crisis reached desperate levels as the standard cabins struggled to maintain barely survivable interior temperatures despite continuous stove operation. Miller's group burned through 9 full cords of split pine during the 30-day period, requiring daily woodcutting expeditions in dangerous weather that left one miner with severe frostbite on 3 fingers. Their dawn interior temperatures averaged 40 degrees Fahrenheit, even with fires banked throughout the night, forcing occupants to sleep in full winter clothing and creating condensation problems that froze bedding solid by morning. Food storage became critical as the prolonged cold overwhelmed the minimal insulation provided by standard cabin construction. One cabin lost approximately 1 bushel equivalent of dried supplies when storage containers inside the structure froze solid at temperatures below minus 10 degrees Fahrenheit, demonstrating that proximity to a heat source provided no protection against systemic thermal failure in poorly insulated buildings. The work capacity losses mounted as cabin occupants dedicated increasing time to basic survival tasks rather than productive mining activities. Miller's group lost at least 4 full work days per week to woodcutting, snow removal, and emergency repairs, reducing their effective mining time by over half during the critical late winter period when accumulated or needed processing before spring runoff made creek crossings impossible. Henry's integrated shelter system demonstrated its full capabilities during this ultimate environmental stress test. His interior temperature reading stabilized at 70 degrees Fahrenheit throughout the 30-day period, including nights when external conditions reached minus 20 degrees Fahrenheit with sustained winds that created whiteout conditions and threatened to collapse less robust structures in the area. The fuel efficiency of Henry's system proved decisive during the extended emergency conditions. He consumed exactly 2 cords of split pine over the entire 30-night period, achieving this remarkable efficiency through the combined effects of his floor insulation, double-wall envelope, and controlled ventilation systems working together as an integrated thermal management approach that maximized heat retention while minimizing waste. The structural integrity of Henry's tent platform system excelled under extreme loading conditions that damaged conventional construction throughout the region, His raised log foundation remained completely stable with no frost heave damage, while the perimeter trench system prevented snow drifting from accumulating against the tent walls and maintained clear drainage around the entire structure perimeter. Most significantly, Henry maintained full work capacity throughout the crisis period, while his neighbors struggled with basic survival tasks. He lost 0 days to emergency repairs. Fuel gathering occupied only 2 hours daily compared to 6 hours for cabin dwellers, and his comfortable interior conditions allowed normal rest and recovery that sustained his physical capacity for mining work during the limited daylight hours. The performance differential reached levels that could no longer be dismissed as coincidental or site-specific advantages. Henry's interior maintained a 90-degree temperature differential above external conditions, while neighboring cabins achieved only 60-degree differentials, representing 50% superior thermal performance, despite using less than quarter the fuel consumption of standard construction methods. The dramatic contrast in repair costs highlighted the economic advantages of properly engineered shelter systems. Henry spent $0 on emergency maintenance during the 30-day crisis, while cabin occupants invested over $40 each in materials and supplies for midwinter structural repairs that barely restored minimal functionality to damaged buildings. When the extreme weather finally moderated in early March, John Miller and 2 other neighboring miners visited Henry's tent to experience the comfortable interior conditions firsthand. Miller touched the warm canvas walls, felt the stable floor temperature, and observed the steady heat output from Henry's efficiently managed stove system, before admitting that he would consider building a similar shelter for the following winter season. The quiet vindication spread beyond the immediate mining district as word of Henry's success reached supply centers and established mining operations throughout the Colorado high country. The general store in Leadville noted that a heavy canvas wall tents with stove jacks sold out completely during the spring ordering period, indicating growing interest in alternative shelter approaches among experienced miners who had witnessed conventional cabin failures. 3 miners working claims within 10 miles of Henry's location adopted modified versions of his double-wall, hay-insulated tent system during the 1897 season. Their implementations varied in specific details, with some using wool blankets instead of hay for insulation and others experimenting with different ventilation configurations, but all incorporated the fundamental principles of floor elevation, envelope insulation, and controlled air management that Henry had demonstrated. By 1902, a mining supply company circular included references to insulated wall tents as cost-effective winter shelter options for remote camps, describing techniques that bore clear similarities to Henry's integrated system. The circular noted fuel savings of up to 60% compared to standard log construction, along with reduced maintenance requirements and improved occupant comfort during extreme weather conditions. The legacy extended beyond immediate practical applications to influence broader understanding of high-altitude shelter design principles that would benefit mountain workers for decades to come. Henry had proven that systematic thermal engineering based on traditional knowledge could outperform conventional construction methods that prioritized appearance and familiar materials over actual performance in harsh environmental conditions. The core lesson transcended specific construction techniques to demonstrate that real shelter effectiveness depended on understanding and controlling the fundamental mechanisms of heat loss, rather than simply building heavier or more expensive structures that failed to address the root causes of thermal failure in extreme mountain environments.